Okay, let's talk a little bit about the arrangement of electrons around an atom. I guess your first question might be, why do I care? Well, as a chemist, you care because really, when you talk about chemistry, it's all about the electrons. When you take two atoms and you put them together, they're not going to touch at the nuclei because the charges are so high, you just have to force them together. You just can't get that much energy at room temperature. It's just not going to happen. But there is enough energy at room temperature to make them touch at the electrons. So you've got this atom over here, which has a negative shell of electrons around it. And you've got another atom over here that has a negative shell of electrons around it. They're negatively charged, and so, yeah, they're going to repel. And so you have to add enough energy to kind of force them together. But that is doable, and that's something called the activation energy, which maybe we'll talk about in the future. But once you get them together, then they're going to go ahead and react, and you end up with a chemical reaction. So do you see, if I know something about how the electrons are arranged around this atom, and I know something how the electrons are arranged around this atom, particularly the outer electrons, because that's where they're going to touch, is at those outer electrons, then that's going to give me some insight into how things are going to chemically bond. All right, so knowing how the electrons are arranged gives me some insight into reactivity, which as a chemist is what I'm interested in. And since it's going to be on your test, I guess you're probably kind of interested right now too. So grab your Chapter 2 notes. There should be some notes online that I put on that I actually filled in for you. It's a PDF file. If you haven't downloaded those yet, just go ahead and do that right now. I'll wait. Put it on pause. Okay, I guess you've done it. And what we'll do is we'll just kind of go through those and I'll explain things as we go. All right, so I guess let's go ahead and get started. Okay, so we are starting right here, arrangement of electrons around the atom. All right. Electrons are arranged in energy shells, also known as energy levels sometimes. And those energy shells are made up of energy subshells, which are sometimes called sublevels. The General Chemistry book calls them sublevels and energy levels, and you will hear me accidentally go back and forth between that terminology and the shell subshell thing, but it's talking about the same thing. Those subshells are made up of orbitals, and within an orbital, an electron can have one of two spins. That is the overview of what we're going to talk about in this particular video. It's a little confusing if you've never seen it before. It just seems like a bunch of rules. That's because it is a bunch of rules. All right. It comes from some very complex mathematical equations that you really don't want to see. What I'm giving you basically is the answers. I'm not giving you the question and then the answers. So it's like if you turn to the back of the book and you saw the answer to a problem, number 47, 32 grams. It doesn't seem to make a lot of sense there, unless you know the problem. But it is the answer. So I'm kind of giving you the end result of a lot of things that come out of some complex mathematics that we just really don't have the time, the inclination, and quite frankly, in my case anyway, the intelligence to do justice. So I'll just kind of toss out as what I can without using any calculus as we go along. It kind of helps if you kind of think of it as a hierarchy, I think, to help kind of organize the whole thing together. So let's say, for example, you decide you want to go to Six Flags over in Dallas. So you go out there and you park your little Honda SUV out there with 20,000 other Honda SUVs, and you get on that little loop-de-loop roller coaster and go around that 3 or 4 times till you're too dizzy to walk. And about 8 hours later, you go out to the parking lot and you try to find your car. All right. Well, kind of hard to do in such a large parking lot. I get lost in Walmart parking lot occasionally and kind of wandering around trying to find my car. I have no chance at Six Flags. Fortunately, the folks at Six Flags kind of thought of this. So what they did is they kind of divided the parking lot into sections for you so that you can have a fighting chance of finding your car. So for example, maybe at Six Flags, there's 5 or 6 or 7 different parking lots that the entire thing is divided into. And so you've got a blue parking lot, a red parking lot, and a green parking lot, and so on and so forth. So let's say, for example, you're parked in the blue parking lot. Well, there's a lot of cars parked in the blue parking lot. So what they do is they divide that into sections. So maybe section A, section B, section C, section D, so on and so forth. So let's say you're in the blue parking lot and you're parked in section A. Well, it's still a pretty big section. So what are sections made of? Well, sections are made up of rows. All right. So maybe they number the rows. So you're in the blue parking lot, section A, row 23. Well, what are rows made up of? Well, they're made up of spaces. So maybe you're parked in the blue parking lot, section A, row 23, space 4. There's lots of space 4s out there. There's lots of row 23s. But there's not a space 4, row 23, in section A, in the blue parking lot. There's only one space that has all 4 of those numbers. And if your car is parked there, now you have a fighting chance of remembering where you parked. Make sense? Well, it's kind of the same way with electrons. Electrons are found in energy shells, and those shells are divided into subshells. Within those subshells, these are made up of orbitals, and within an orbital, an electron can have 1 of 2 spins. So if you think of it as kind of a hierarchy, like our parking example, I think it makes it a little bit easier to kind of wrap your mind around the whole thing. All right? So I guess let's just go ahead and start with the energy shells. Seems like a good place to start. So electrons are arranged in certain discrete energy shells outside the nucleus. Okay, the maximum number of electrons in any given shell is given by the formula 2n squared. All right, so in other words, electrons are arranged in energy shells outside the nucleus, and you can be in the first energy shell, you can be in the second energy shell, you can be in the third energy shell, and so on and so on and so forth. All right, it's always a whole number. It's like stairs on a staircase. You can be on the first step, you can be in the second step, third step. You can't be on the 2.5 step. You'll fall down if you try to do that. Well, it's kind of the same way here. Electrons are either found in the first energy shell, or the second, or the third, or the fourth. Certain discrete energy shells outside the nucleus. All right? The maximum number of electrons in any shell is given by this formula. Imagine, for example, Midland College. You've got parking lots all over Midland College. You've got some over by the Shap Center. You've got some over here by the administration building. You've got the Fox Science parking lot. And all these parking lots hold different numbers of cars. You have big ones, you have little ones. Well, it's kind of the same way around an atom. All right. The way you tell how many electrons are in an energy shell is use this little formula 2n squared. So if I'm interested in the first energy shell, I plug in a 1 there for n. So 1 squared is 1. 1 times 2 is 2. So I can fit 2 electrons in the first energy shell. So it's kind of like a parking lot that holds 2 cars. Not very big. All right, second energy shell, plug in a 2. 2 squared is 4. 4 times 2 is 8. Okay, so I can put 8 electrons in the second energy shell. All right, 3 squared is 9. 9 times 2 is 18. 18 electrons in the third energy shell. 4 squared is 16. 16 times 2 is 32. 32 in the fourth. 5 squared is 25. 25 times 2, 50 electrons in the fifth energy shell. Do you see a trend here that's forming? Notice as you go up in energy shells, the number of electrons you can fit in each successive energy shell is larger and larger and larger. And the reason why is because close to the nucleus, where that first energy shell is, there's not a lot of room. It's real crowded. So if you start trying to cram a bunch of electrons in there, they get too close to each other, they're going to repel. All right. The second energy shell is a little further out, and so therefore you can fit more electrons before the crowding starts. Third energy shell further out still, fourth energy shell even further out, and so therefore each energy shell can hold more electrons. So it's like different parking lots here at Midland College. Some of them are kind of tiny, some of them are kind of large. All right. Generally speaking, an electron would prefer to be in a lower energy shell. Lower energy shell means closer to the nucleus. When we talk about closer average distance to the nucleus, that is analogous to saying lower in energy. So an electron close to the nucleus is low in energy. An electron further away from the nucleus is high in energy. All right, well, if electrons prefer to be in the lowest shell, that would be shell number 1, which holds how many electrons? 2. So if you have an atom that has 57 electrons, you can't park 57 cars in 2 spaces. It just doesn't work. All right, so the rest of them are going to have to do something else, and we'll talk about it. But that's kind of the way it works. So when you hear average distance close to the nucleus, think low in energy. And that's where the electrons prefer to be. When you see average energy large distance from the nucleus, that means high in energy. Electrons would prefer not to be there unless they had to. Okay? All right. Well, energy shells are divided into energy subshells. And your subshells are made up of orbitals. All right? So each shell can have subshells made up of orbitals. An electron in an orbital can have one of 2 what we call spins. All right, we'll talk about that in a minute. So let's talk about the subshells. So the lowest energy subshell that you can have is something called an S subshell. All right, each energy shell has an S subshell containing one what we call S orbital. All right, S actually comes from the word sharp. It's a spectroscopic term. They looked at light being given off from certain substances, and there was a particular line on a particular spectrum that was very bright and sharp, and it was a transition from an S subshell. So that's where the S comes from. It's just, kind of a history thing. Don't worry about it. Okay? Any energy level can have an S subshell. Any energy shell. See, I told you I would do it. All right? Each S subshell here contains one S orbital. All right, so if you saw a picture of an S orbital, that is the subshell. See, 2 electrons can put into an S orbital, and in fact, it turns out what you're going to find is any orbital. I don't care if it's an S, a P, a D, an F, an sp2 hybridized orbital, a molecular orbital, anti-bonding, non-bonding, bonding molecular orbital, 2 electrons. Every orbital always holds 2 electrons. Okay? So 2 electrons can be put into that S orbital for a total of 2 electrons in that subshell. All right? Would you like to see what an S orbital actually looks like? Where do we get this from? Well, electrons have some wave-like properties as well as particle-like properties. And it turns out for a wave, you can actually write an equation that will describe that wave. All right, and so you can actually write an equation for an electron. All right, the equation is very complicated. You don't want to see it today. But the gist of it is, what I can do is I can take that equation, which we call the wave function of that electron, and I can square it, okay, or multiply it by its complex conjugate technically, but we're gonna call it squared for our intents and purposes. What you get is you get something called a probability function. All right, and if you take that probability function and you graph it, what you get is you get a region of space where the electrons are most likely to be. All right, so in quantum mechanics, what we can do is we can express in terms of probabilities where the electron is most likely to be. We can't pinpoint exactly where the electron is. So we can't draw it as a little tiny ball. We can't even draw a little circular orbit. All we can do is we can say with a 95% probability, which is the confidence level that most orbitals are drawn at, the electron is somewhere within this region of space. And that's actually the best we can do. And it has to do with the wave-like properties of electrons as well as the particle. All right? So if I did that and I drew a picture, what I would get is I would get something that looks a lot like this right here. Okay? So it's take this little circle that I drew here and make it into a sphere. Remember that electrons are three-dimensional. They're just like you and me. So they can go this way, that way, up, down, back, forth. And so the graphs that we're drawing here are actually three-dimensional graphs. So imagine a Nerf ball, I guess, sort of. That's what an s orbital looks like. Well, each s subshell contains one s orbital, so therefore, there you go. That's the entire s subshell, because it's made up of that one s orbital. You know, if I've got a parking lot that only holds 2 cars, how many sections do I really need? Well, you don't really need sections if you just got 2 cars there. Well, that's kind of what's going on here. It's such a small energy sublevel or subshell. Yeah, the energy, the orbital is the sublevel, subshell in this case right here. Within this orbital, I can fit 2 electrons. So this is what an s subshell looks like. Now, what's the difference between a 1s, a 2s, and a 3s? 1s means first energy shell, s subshell. 2s means second energy shell, s subshell. Well, the main difference is the size. Your 1s electrons, they spend their time relatively close to the nucleus, and so it's like a small sphere. The 2s electrons are a little bit further out, so it's like a larger sphere. A 3s is even larger still. They spend their average distance from the nucleus even further out. All right. So it's basically size. There's a couple of minor differences there, but that will do for now. So when you think s subshell, think spherical in shape, and 1s is smaller than a 2s, which is smaller than a 3s, and so on and so forth. But same basic shape. Okay? All right. Well, what's next? Well, you can have electrons in a p subshell. All right. Energy shells 2 and higher can have a p subshell. There is no such thing as a 1p. Too low in energy. Only 2 and higher can have a p, containing 3 p orbitals. 2 electrons can be put into a p orbital for a total of, I got 3 orbitals times 2 electrons, 6 electrons in a p subshell. All right. Shape-wise, they look like this. Take this shape that I've drawn for you here in the notes and turn it into like a 3-dimensional shape. So imagine you had a long skinny balloon and then you grabbed it right there in the middle and you kind of pinched it and you had like a lobe of balloon coming out up here and a lobe of balloon going down there. That's kind of what a p orbital looks like. Okay? 2 electrons can be put into this p orbital. Does that mean one of them is here and one of them is here? No, doesn't mean that. It just means somewhere within that region of space, I can fit 2 electrons. They both might be here, they both might be there, they might be here and here at the same time. Yeah, that's the best we can do. Kind of weird, huh? All right, but we said there were what? 3 of them. So what does the other 2 look like here? Well, when you're making orbitals for a subshell, one of the requirements is they have to be degenerate. Degenerate means they have to have the same energy. Same energy, same average distance from the nucleus, equally likely to be populated. That's essentially what it means. All right. The other requirement is they have to be orthonormal here. Ortho here, normal means the wave function is normalized. In other words, the probability of finding an electron within the universe is 100%. It's not 50%. It's not 150%. Don't worry about normalizing wave functions. Not necessary here. The ortho part is kind of important, though. Orthogonal, of course, the ortho means, orthogonal basically means at right angles to each other and not overlapping. And that's the simple definition. So essentially what I want is I want another orbital that looks like this, is at right angles to it, and does not overlap. Well, one way I could draw it is I could draw one this way, sideways, and draw one up and down. See? That's at right angles, and it's not overlapping. Each of those orbitals are equally likely to be populated because they're the exact same size, and they're actually the exact same shape. The only difference is one's turned that way, one's turned that way. See? And so that's your second p orbital. But how do I get a third p orbital that is right angles to the other 2 and not overlapping? Well, imagine you had a lobe here that is going straight towards you. And then imagine you had a lobe that was going straight back behind you, back there. All That's your third p orbital. Remember, again, electrons have 3 dimensions of space to roam in, not just a flat piece of paper like we've got drawn here. See? And so, yeah, you've got 3 of them. And so what you end up with is you end up with something that looks kind of like a jack. You've got this one up and down. You've got this one side to side. This represents one lobe coming out towards you and one lobe going back away. I know, bad art. Not an artist. That was my mom, not me. We'll make this little orbital striped. We'll make this orbital polka dotted. Or orbital's really polka dotted. Well, I don't know. You ever see an orbital? Can't prove me wrong. And we'll leave this one plain. Okay? 2 electrons can fit into this. 2 electrons can fit into this X orbital, this piece of X here, and 2 electrons can fit into this one. This is my piece of X because it lines up along the X-axis. This is my piece of Y because it lines up along the Y-axis. In 3-dimensional coordinate math, we usually reserve the vertical axis for the Z-axis, and so this is my piece of Z. 2 electrons here, 2 there, 2 there, 6 electrons in a p subshell. Each of these orbitals is equally likely to be populated, equal in energy, because really the only difference is one's turned that way, one's turned that way, one's turned that way. Same size, same shape. Make sense? The difference between a 2p, a 3p, and a 4p, again, is just size. The 2p is a small jack. The 3p is a larger jack. The 4p is even a larger jack. Larger jack means electrons spend their average distance from the nucleus further away, higher in energy. Smaller jack means the electrons spend their average distance close to the nucleus, lower energy. That's the difference. Okay? All right, let's move on then. Energy shells 3 and higher can have a D subshell. Okay, by now you should be seeing a trend. We'll talk about it. Energy shells 3 and higher can have a D subshell containing 5 d orbitals. 2 electrons can be put into a d orbital for a total of, I've got 5 orbitals times 2 electrons, 10 electrons in a d subshell. All right, do you see the trend here? All energy levels can have an S, 2 and higher can have a P, 3 and higher can have a D. Do you see that? Okay. How many S's were there? There was 1. How many P's were there? 3. How many F's? 5. Do you see it's going up by 2 each time? How many electrons can I put in the d orbital? 2. Any orbital always holds 2 electrons. Notice that the number of electrons in each successive subshell is going up by 4 each time. We went from 2 to 6 to 10. Why is it going up by 4? Well, because the number of orbitals is increasing by 2 each time. And any orbital always holds 2 electrons. 2 times 2 is 4. So the reason each successive subshell here contains more electrons is not because the orbitals hold more. It's because I have more orbitals. All right? By the time you get up to 5, remember the requirement is they have to be degenerate, same energy. Is there any requirement that says they have to have the same shape? No, they just have to have the same energy. So imagine if I gave you 4 pennies. That's 4 cents. Could I give you 4 cents any other way? No, that's pretty much it. 4 pennies is 4 cents, right? But imagine I wanted 6 cents. How could you give me 6 cents? Well, you could give me 6 pennies, or you could give me a nickel and a penny. Is that the same amount of money? Yeah. If I gave you 6 pennies and you gave me a nickel and penny, would we be even? Yes, we would. What if I asked you to give me $1.67 in change? Well, you could give me 167 pennies, I guess. You could give me what? 4, 5, 6 quarters, a dime, and 16 pennies or 17 pennies. You could give me, well, you get the general idea, 16 dimes and a nickel and 2 pennies. Lots of different ways to make $1.67. You see, the more money we have, the more different ways I can stack coins together and get that amount. Well, it's kind of the same way with energy here. The higher up I go in energy, the more shapes I can have and still have the same amount of energy. So with your S's and P's, there's just one. But with Ds, there's actually two different shapes. One of them looks like this right here. It's like a p orbital with a little ring of electron density around the middle. I call it the Saturn of p orbitals here. This is your dz squared orbital, if you just really care. And turns out within that region of space, I can fit 2 electrons, because any orbital holds 2 electrons. The other 4 look like this cloverleaf shape here. This is not all 4 of them. This is one of them. Okay, so I've got one orbital that looks like this. I got 4 lobes on it, so that means I get 4 electrons in there, right? No. 2 electrons can fit into this 4-lobe shape. The difference between this one and the other 3 is just the way they're oriented. One is this way, one is this way, one is that way, and so on and so forth. All right. I am not going to attempt to draw those together because I just cannot do it. Maybe you can find a picture in your book somewhere, but yeah, this is as good as I go right here. All right. So yeah, find a nice picture in your book or on Wikipedia or something like that. But yeah, the other 4 look like this. So one here that I can put 2 electrons in. 4 of these that fit 2 electrons apiece. 2 plus 8 is, there's your 10 electrons. Okay? All right. Technically, there are an infinite number of energy subshells. Technically an infinite number minus 1, but an infinite number of energy subshells. There is a practical limit to how high up you need to go. Fortunately, we are reaching that practical limit. So I'm going to show you one more. And actually, you could keep going if you wanted to because you know the trend by now. Okay? Energy shells 4 and higher can have an L subshell. See, we went S is all, P is 1 and 2 and higher, D is 3 and higher, F is 4 and higher, containing 7 F orbitals. Notice it's going by 2 each time. 2 electrons can be put into an F orbital for a total of 7 times 2, 14 electrons in the F subshell. Notice the number of electrons is going up by 4 each time. 2 more orbitals, 2 electrons apiece. That's why it's going up by 4. All right. There are 2 shapes here. And yeah, I'm not good at this. 2 of them actually look like this. It's like a p orbital, but it actually has 2 rings of electron density around it. And so I can fit 2 electrons in each of those. The others are this 6-lobe shape, actually. And you got 6 lobes, but you can only fit 2 electrons in that. So if I remember correctly, 2 of them kind of look like this. The other 5 look like that. Put all that stuff together, and what you end up with is you end up with an L subshell. And that's the way it works. Past this point, you go to G, and then you go to H. They skip I and J for some reason, probably because those are what you usually use for your eigenvalue vectors, I and J, and they go to K, and then after that it goes in alphabetical order. All right, and those exist, but there's a reason why you don't really need to know those. If you can make it up to F, you're going to be okay. So S, P, D, F. Look them over. Do the best you can to kind of get that together in your head. I know it's confusing first time you see it, but do the best you can. We are going to use this, trust me. Hopefully it will get less confusing as we go on and we start talking about why it's important. Okay? All right, well, how are we going to use that? What am I going to do this for? What am I going to use this for? Well, we're going to talk about something called electron configurations. All right, electron configurations show the total number of electrons in an atom and their energies. Once we know something about the structure, now we can start figuring out where the electrons are around an atom. So maybe I've got an oxygen atom and it's got 8 electrons. Well, before what we did is we just drew them in some sort of big giant electron cloud. And I said we could do a little bit better than that, right? Long time ago? We can. There are places where those 8 electrons are more likely to be. And that's what we're going to do in the next video, is we're going to start building atoms. We're going to start putting the electrons in. Once we figure out where they are, then we're actually going to figure out what that means and how we can use it. And so, congratulations. That's video 1. So next time what we'll do is we'll talk about electron configurations and something even more fun than that, orbital diagrams, which is kind of like an electron configuration on steroids, and we'll go from there. So I guess we'll see you in the next video. Bye for now.